Hi, this is Remembering the Past, the show where we talk about people who've died recently who've had a profound effect on our history, our society, or our culture. And in our ongoing series on Nobel Prize winners, tonight we're going to talk about Val Fitch, who died recently at the age of 91. Val Fitch was a theoretical physicist who won the 1980 Nobel Prize in Physics along with James Cronin. Val Fitch was born and raised in Nebraska. He did most of his important work at Princeton. Before that, he was at Columbia, but he was recognized as a talented physicist as a young man, and he was sent to Los Alamos, where he was one of the young scientists working on the development of the atomic bomb. And actually, I think the best part of his story is there, but we'll start with his Nobel Prize. And look, I didn't do that well in high school physics, so this theoretical physics is way beyond me. Fitch and Cronin got their Nobel Prize for discovery of violations of fundamental symmetry principles in the decay of neutral K mesons. Now, as best I can ascertain, the universe is made up of matter and antimatter, and everybody thought that they were completely symmetrical. They were charged particle or CP symmetrical, and what Fitch and Cronin found out was that they were not symmetrical. It's called a CP or charged particle violation. So matter and antimatter are not mirror images of each other. This also meant that the widely believed concept of time symmetry, that is, if you sent everything backwards, everything would work out the same, was not true either, and there could be variations on what would happen if you could go back in time. And all this has implications for the creation of the universe and the Big Bang Theory, why matter and antimatter didn't just cancel each other out, and why there's a lot more matter than there is antimatter. Like I say, I don't understand it, but here Val Fitch tries to explain it to an interviewer.
If we turn to the work for which you were awarded the Nobel Prize in Physics together with James Cronin, this was the demonstration of CP violation. Am I right in thinking that what symmetry violation tells us is that the laws of physics exhibit some kind of handedness?
Well, that's true of parity. Associated with the parity violation was a theoretical theorem, TCP theorem, purely theoretical construct. You couldn't devise a theory of quantum mechanics or anything without invoking the TPC theorem. That is, all interaction should be invariant under the combined operations of time reversal, parity, and charge conjugation, TC. So as soon as there was CP violation described, that people eventually had to accept. I mean, it was difficult to accept because people did not like, physicists did not like the idea of a violation of time reversal. If you reverse the direction of time, why, all interactions should remain the same. They shouldn't change. And here was a case where apparently things did change when you reversed the direction of time. So that was a great stumbling block for physicists to accept the idea of CP violation.
Because the time reversal phenomenon, if you sort of bring it to a practical example, is something like a chemical reaction where things combine and things can uncombine.
Right.
And it should, the same principle, the same laws of physics should apply.
You learn chemistry. Analog is very good. You have A plus B going to C plus D, but the arrows going one direction are always precisely the same as the arrows going the other, which means the reaction rates are the same. And that's what had always been believed to be true. Now we know it isn't quite true. I think it took the Nobel Committee some time to digest the implications of the discovery. But after that discovery, then people immediately accepted parity violation, but CP conservation, that had to go with it. That was part of the dogma, theoretical dogma from 57 to 64 when this discovery was made.
So understanding CP violation has offered an explanation of why there is or a partial explanation of why there is an imbalance of matter and antimatter in the universe. That imbalance was known before symmetry violation was ever found. So why was it that everybody accepted the invariance of symmetry prior to there being...
Because that unbalance, the implications of that imbalance between matter and antimatter and the abundance of matter and antimatter in the universe had just never been thought of in those terms. Actually, it wasn't until Sakharov pointed it out in 1967, as I recall, that the connection was drawn.
Right.
So it's true, the first discovery of CP violation was really the discovery that there was more matter in the universe than antimatter, much more. But it wasn't recognized then in those terms. It took Sakharov to point it out. If you try to calculate how much matter, antimatter, as symmetry there should be in the universe on the basis of the CP violation observed in the laboratory, you're off by many orders of magnitude. That is something that the theorists have not succeeded in doing yet, calculating the magnitude of that asymmetry on the basis of the laboratory measurement.
Okay, so you get the idea. So unless you're a theoretical physicist or somebody who's really interested in that stuff, the most interesting part of Val Fitch's career from my standpoint was his observation on the great physicists and personages that he came into contact with. For instance, you heard him talk about Andrei Sakharov there, and that's one of the few times you hear Andrei Sakharov mentioned for his physics rather than his politics. Here Fitch talks about Einstein. I'm not sure if he ever met him. Maybe he did at Princeton. The interviewer should have asked that. But he talks about Einstein's theory of relativity, which was actually two theories, the special theory of relativity and the general theory of relativity, and how they had to be validated by experiments and observations, or else they were nothing more than theories, which is currently the difficulty with the string theory.
Everything in physics is dependent on experiment in the end. That was one of the great things about Einstein. When he proposed his general theory of relativity, he also proposed 3 experimental tests. And that's been a model for what a good theory should be ever since. Unless there are experimental tests that can be conducted to check out an idea, then the idea doesn't hold much credence in the community.
And it was a long time until the third test was performed. It was 1919, wasn't it, the solar eclipse one?
Well, 1919 was the first one, of course, when the bending of light around the sun. Of course, there was the precession of the perihelion in Mercury, which agreed with the theory very nicely. That's a rather beautiful test. The difficulty of string theory is that it deals with such high energies, such small distances, that it's hard to, essentially impossible to dream of an experiment that might check it.
Well, as I said before, not being a theoretical physicist, I think the best part of Val Fitch's story is how he worked at Los Alamos when he was a young scientist.
For me, at that stage of my career, it was just a perfect Army assignment. Being put in contact with superb scientists and doing many things with them, socially as well as in the laboratory, was a great experience for me. And it was then I really decided to concentrate on physics. One of the people I met at Los Alamos was actually Rabi. I didn't meet him at Los Alamos. I actually met him out in the desert, Alamogordo, during the testing days. And one of his colleagues during the days when he was doing atomic beams at Columbia was J.M.B. Kellogg, and Kellogg was head of the physics division at Los Alamos. He was, I guess, the principal reason I went to Columbia for graduate school. He wrote me a nice letter of recommendation. And Rabi at that time was chairman of the department. So when I went in to see the chairman to try to get into graduate school at Columbia, I reminded Rabi of this letter, and the secretary pulled it out. And he immediately got on the phone and called Jim Rainwater, who was doing cyclotron research at Columbia at the time, and basically assigned me as a research assistant to Jim Rainwater. I followed that all the way through graduate school. As you know, Rainwater later got a big prize himself.
James Rainwater won the 1975 Nobel Prize in Physics. Here Val Fitch tells a great story about witnessing the first atomic bomb test.
One cannot really describe it because it's so impressive. My first comment after the thing went off was to an MP who was at the door of the main control bunker. I don't know why he was there, but he was supposedly to control access, but he wouldn't know who was to be let in and who was not to be let in. After the explosion, no one had told him what to expect, and he was just totally white. So my comment to him was that the war will soon be over, and of course it was.
Well, one of the fascinating stories of the Manhattan Project is the interplay between J. Robert Oppenheimer, the director of the project, and Edward Teller, who became his nemesis after the war was over. Here's Fitch's personal recollection of Edward Teller.
I also took one from Teller.
Really?
I stayed there for 2 lectures. I was never one to appreciate Teller. I can tell you right from the start. He has such a high opinion of himself, and you quickly discovered that after the second lecture he had lieutenants doing the lecturing. But during the first 2 lectures, he had already found his favorites in the course. They turned out to be sons of friends of his. Teller is, he did brilliant work in the early days, but then with the H-bomb thing and the Oppenheimer, he seemed to have gone completely off his rocker, in my opinion. Became a reactionary of the first order, and didn't really recognize nonsense.
And even
that's one man's opinion.
So at Los Alamos he was heading in a different direction already, wasn't he?
Well, He was insulted at Los Alamos because Oppenheimer did not choose him to head the theoretical division. And so he went off and sulked, basically. And Oppenheimer gave him something to do to keep him out of the way, and which was to work on a super. And that's what he did, to no avail. But
a super, that's the H-bomb.
Yeah. So that's how he came to work on the super at Los Alamos. He was just pouting. And I probably know it was Hans Bethe that was selected to head the theoretical division. And that was Oppenheimer's signs of geniusness in dealing with people. He knew how to pick the best ones. Not people like Turner, people like Bethe.
Well, Fitch mentions Hans Bethe, who was a fantastically talented physicist also. And here Bethe talks about Oppenheimer and indirectly about Teller. He doesn't mention him by name, but you can sort of guess that's who he's talking about. Bethe is talking about Oppenheimer here.
I was the chief of one of 8 divisions, namely the Division of Theoretical Physics. We did calculations concerning the size of the bomb and the action of the bomb, the energy you might get from it. He was a very brilliant man, and I think nobody else could have directed the Los Alamos laboratory as well as he could. He understood everything, where the slightest indication of what was being done or what was the difficulty would immediately be understood by him, and he took immediate action to improve matters. So just by his brilliance, he was able to keep together this collection of quite competent and inventive people, which nobody else could have done. He was in favor of limited containment. Many people in the government, and especially in the Air Force, were very much on the other side, and therefore they wanted to destroy Oppenheimer's influence. And unfortunately, he had a weak spot in the past. He had been very sympathetic to the communists, and at the time that was a great mark against him. So he was an easy person to destroy.
Bethe didn't like Teller, and Teller and Oppenheimer had a love-hate relationship. But in 1953, there was a hearing to determine whether Oppenheimer was a security risk. Most of the scientists didn't testify against him, but Teller, after giving generally complimentary testimony, said 24 words that changed both their lives. His final statement was, "I feel that I would like to see the vital interests of this country in hands which I understand better and therefore trust more." Oppenheimer lost his security clearance, and many of the great physicists refused to have anything to do with Teller after that. Fascinating story, and we'll probably go into detail on it more sometime. Anyway, back to Val Fitch. He was finally asked whether physics has become too complex for the tabletop physicist, whether you need a big conglomerate to do physics today.
Is there nevertheless a place for the sort of, I don't know if you call it low-key approach that you used, the smaller teams, smaller budgets, if you like, in experimentation?
You mean tabletop as opposed to exactly. CERN scale? Certainly not in high-energy physics. But there are a few tabletop experiments around which have been revealing fundamental processes, but they are hard to come up with, there's no doubt.
And that CERN that Fitch was talking about there is the huge particle physics laboratory located in Switzerland. So to a certain extent, Val Fitch was the last of his breed. Well, I'm going to close on that note. I want to thank my producer and IT genius, Sid Tepps. And it was a little hard coming up with a final song tonight. But since Val Fitch dealt with matter and antimatter, to honor Val Fitch, I thought we'd use a song by somebody who sang about matter. Charles Hardin Holly from Lubbock, Texas, otherwise known as Buddy Holly, who sang with the Crickets, "It Doesn't Matter Anymore."
Well, you go your way and I'll go mine. Now and forever, till the end of time, I'll find somebody new. Baby, we'll say we're through and you won't matter anymore. You won't matter anymore.